Good morning, dear students. A warm welcome to all of you for our today's online revision session for the subject Science and Technology Section A. Yesterday, we have revised chapter number 6 and 7 for Section B. Today, quickly we are going to revise chapter number 1 and 2 from Section A, that is Laws of Motion and Work and Energy. This is our second revision before the first online assessment. So we will not revise the derivations and all. We are only going to revise the topics quickly. So we begin with the first chapter, Laws of Motion. To begin with the first topic for laws and motion, we have two definitions here. One is distance and displacement. What is distance? It is the length of the actual path travelled by an object in motion while going from one point to another, and displacement is nothing but the minimum distance between the starting and the finishing points. Here we had seen a small example. Here is the school. Here is Sheetal and Prashant's house. Here is Sangeeta's house. So the actual path which is followed, this is path A and path B to reach the school, that is distance. And the shortest distance between the Sheetal and Prashant's house and the school is displacement. As both of them involve the length of the total distance covered, the units of both distance and displacement, they are same. Our next topic for this chapter is speed and velocity. What is speed? Speed is the total distance travelled upon time which is required. And what is velocity? It is also the distance travelled in one direction by an object in unit time is called its velocity. So for speed, it is distance upon time, and for velocity, it is displacement upon time. Here also, if you see, the units of both speed and velocity are same. What is the basic difference between speed and velocity is speed does not involve any direction, whereas in velocity a particular direction is to be followed. So speed is a scalar quantity, whereas you can say velocity is a vector quantity. So speed is distance upon time, velocity is displacement upon time. If you know, the units of both distance and displacement are same, hence the units of speed in MK system is meter per second, and velocity also it is meter per second. CGS system it is centimeter per second, and for velocity it is also centimeter per second. So units for both speed and velocity are same. Our next topic is acceleration. What do you mean by acceleration? You have seen a very small example during your explanation that all of you have witnessed playing on a slide in a park, and you know that while you are sliding down, the velocity is less at the top, it increases in the middle and becomes 0 towards the end. So what is this rate of change of velocity at every point? The rate of change of velocity is called nothing but acceleration, and for formula of acceleration it is change in velocity upon particular time. So if the initial velocity of any object is u, and in time t it changes to a final velocity v, then acceleration is nothing but change in velocity, means final velocity minus initial velocity upon time. So if acceleration is denoted by small a, it is v minus u upon t. So acceleration is nothing but rate of change of velocity. So the three types of acceleration we are going to quickly revise. The first is positive acceleration. When the velocity of an object increases, then the acceleration is positive. When the velocity of an object decreases with time, it has negative acceleration. Negative acceleration, it is also called as deceleration, and its direction, if you see, is opposite to the direction of velocity, whereas in the first case the acceleration is in the direction of velocity, and the third case is if the velocity of the object does not change with time, If it is constant, then the body is said to have zero acceleration. So this you have to remember for MCQs: positive, negative and zero acceleration. The next two definitions are uniform and non-uniform motion. Uniform means constant. If an object covers equal distances in equal intervals of time, it is said to be in uniform motion. And if an object covers unequal distances in equal intervals of time, it is said to be in non-uniform motion. So if an object is covering same distance, that is equal distance, in same time intervals, then we can say that it is moving uniformly. But when unequal distances are covered in equal intervals of time, then we can say it is in non-uniform motion. Here we had taken a very good example about the distances covered by Amar, Akbar and Anthony. For a very good example of non-uniform speed or motion is the motions of vehicles being driven through heavy traffic. That time the vehicle does not move in a uniform way. The motion is non-uniform. Our next topic is equations of motion using graphical method. Here we had seen how Newton studied the motion of an object and gave us a set of 3 equations of motion, and these equations relate the displacement, velocity, acceleration and time of an object moving along a straight line. As I had told you, all these 3 equations of motion are very important and they should be remembered by you not only in the 9th standard but ahead also if you take physics as your main subject. So here you have to consider an object which is in motion along a straight line with initial velocity u. After a certain time it will attain a final velocity v due to the acceleration a, and the displacement in that particular direction is small s. The 3 equations of motion can be written as these 3 equations. Remember carefully. You have also seen how they are useful in chapter number 2, work and energy, to derive the expression for kinetic energy, or we have seen how they are useful in deriving other different concepts. So the first one is v, that is final velocity, is equal to u, initial velocity, plus a into t. So this gives us the relation between velocity and time. Next one is s, that is displacement, is equal to ut plus half at square, which gives us the relation between displacement and time. And the third one is v square is equal to u square plus 2as, gives us the relation between displacement and velocity. So these 3 equations, register it permanently in your minds. Next small definition is about uniform circular motion, the motion of the blades of the fan which you see every day. Let us see what is uniform circular motion. When you speak about uniform circular motion means motion of any object along a circular path is called as circular motion. And when an object is moving with a constant speed along a circular path, then such a type of motion you call as uniform circular motion. The different examples which you experience around you is the motion of the blades of a running electric fan, ceiling fan, or the motion of electrons around the nucleus of an atom, or the motion of any point on a bicycle wheel. All these are examples of uniform circular motion. Now we move to the next part of the chapter, wherein we are going to study about the Newton's 3 laws of motion. And you all know that the Newton's laws of motion are the 3 laws that describe the relationship between the motion of an object and the forces acting on it. Even if you see the Newton's first law of motion, it is called as law of inertia, which involves the balanced and unbalanced forces. So let us come towards the Newton's first law of motion, which states that An object continues to remain at rest or in a state of uniform motion along a straight line unless an external unbalanced force acts on it. What does this law state? We had seen n number of examples for this law. A simple example is a duster. A compass box which is lying on a table, it will remain lying on the table unless you are applying any type of force on it, unless you are pushing the compass box, unless you are pushing the duster, or an object continues to be in a state of motion. Suppose a vehicle is moving with a constant speed, then unless and until you are applying brakes, it will not stop. Means an object continues to remain at rest or it continues to remain in a state of motion unless an external unbalanced force acts on it. For example, a marathon runner unable to stop after the finish line. I had told you the participants in the running race, they are running through a very long distance, so their body becomes used to running. So even after the finish line, you will see them that immediately they won't stop. They cover a little distance after completing the finish line. Or a rock at rest on a hilltop, on a mountainside, it will remain to continue at rest unless you are applying any type of force, unless you are pushing the rock, unless you are picking up the rock from that place, it will continue to remain at rest. So these are the n number of examples which tell you about the Newton's law of motion. And before studying this law, we have studied about the balanced and unbalanced forces. We had taken the example of the event of tug of war, which is an event during the sports in the school. What we had seen under that, as long as the forces which are applied by both the sides are equal, that is balanced, the center of the rope is static in spite of the applied forces. On the other hand, what happens? When the applied forces become unequal, that is unbalanced, a net force gets applied in the direction of the greater force and the center of the rope, it shifts in that particular direction. With this we complete the revision of Newton's first law of motion. Now let us move towards the second law of motion. Before that, we had studied one small concept known as momentum. What is momentum? The effect of one object striking another object, it depends both on the mass of the former object and its velocity. This means that the effect of the force, it depends on a property which is related to both mass of the object and velocity of the object, and this property was named as momentum by Newton, which is denoted by capital P. And very simple language, I will describe momentum. It is nothing but the product of mass and velocity of an object. So formula is small m, that is mass of the object, and small v, that is the velocity of the object. It is a vector quantity. Why? Because momentum has both magnitude as well as direction. How is its direction? Its direction is the same as that of velocity. So the SI unit of momentum is kg meters per second and CGS unit is gram centimeter per second. So what does the Newton's second law of motion state? The rate of change of momentum is proportional to the applied force and the change of momentum occurs in the direction of force. Let us quickly have a glance at the force equation. Here you have to consider an object of mass m which has an initial velocity u. When a force F is applied in the direction of its velocity for a particular time t, what will its final velocity become? It will become v. So the initial momentum will be what? Mass into initial velocity. So m into u, and final momentum will be m into v. What is rate of change of momentum? Change in momentum upon time, that is mv minus mu upon t. Taking m common, v minus u upon t. You all know v minus u upon t is nothing but acceleration. So in place of it, we will place it as a. So m into a. So rate of change of momentum is what? Mass into acceleration. What does the Newton's second law of motion state? The rate of change of momentum is proportional to the applied force. So MA directly proportional to the applied force. To remove the sign, we are going to take K, which is the constant of proportionality. So you will get the force equation as mass into acceleration produced in an object. So see the different formulae which we have studied in this chapter. First we have studied the Newton's three equations of motion. V is equal to U plus AT. S is equal to UT plus half AT square. V square is equal to U square plus 2AS. And the fourth formula is F is equal to M into A. And the last, that is the Newton's third law of motion, which states every action force has an equal and opposite reaction force which acts simultaneously. No need of discussing again. We had taken a good example of two students sitting on a bench. If one hits the other one is not going to keep quiet in return. The child will immediately slap the first one. That will be the reaction given in opposition for the action performed by the first one. So what you can infer here is action and reaction are nothing but the terms that express force. These forces are always seen to act in pairs. One force cannot exist by itself. Never ever you have seen a child hitting himself or herself. So force will always act in pairs. Action and reaction forces act simultaneously. To every action, immediately you will see a reaction. They act on different objects. They do not act on the same object and hence cannot cancel each other's effect. Here we had seen a give reason related to this topic. And the last topic is law of conservation of momentum. I have told you the bigger derivations we are not going to take in the revision. There only one small formula you have to remember. M1 U1 plus M2 U2 is equal to M1 V1 plus M2 V2. With this we complete with the revision of first chapter. Now let us quickly revise the second chapter, that is work and energy. Look at the different examples over here. A girl sitting and doing some educational work, a boy kicking a ball, a girl watching a television, and the fourth one you can see a laborer with heavy load on his shoulders. In all these pictures, in which case you can say that the work has been done? If you look carefully at all the pictures, from the physics point of view, work is done only in the two cases. One where boy is playing with the ball and the person lifting a load on his shoulders, and no work is done with the girl who is studying and the girl sitting and watching TV. Generally, any mental or physical activity is referred to as work. When you finish completing your homework, your parents say, "Did you complete your work?" But when we walk or run, the energy in our body is used to do the necessary work. We say that a girl who is studying is working or performing some work, but that is mental work. And in physics, in science, when we talk about work, we deal only and only with physical work. So what is work? Work is nothing but the product of force and displacement of the object. When a force applied on an object causes displacement of the object, then we can say that work is done. So work done is nothing but force into displacement, that is F into S. Now let us quickly look at the units of work. Work is equal to force into displacement. In SI system, the unit of force is Newton and the unit of displacement is meter. So the SI unit is Newton meter, which is called as joule. And in CGS system, the unit of force is dyne and displacement is centimeter. So CGS unit is dyne centimeter, which is called as erg. So the SI unit of work is joule and CGS unit is, you can say, it is erg. What is the relationship between joule and erg? You know that work is equal to force into displacement. 1 Newton is nothing but 10 raised to 5 dyne, and 1 meter, you all know it is 100 centimeter, that is 10 raised to 2 centimeters. So work is equal to force into displacement. So 1 joule of work when you speak is nothing but 1 Newton force applied causing a displacement of 1 meter. Substitute the values. 1 joule is, what is 1 Newton? 10 raised to 5 dyne. Multiply by 1 meter is 10 raised to 2 centimeter. Applying laws of indices. Here there is a multiplication sign. So 5 and 2 will get added. So 10 raised to 5 plus 2 is 7. 10 raised to 7 dyne centimeter. And dyne centimeter is nothing but erg. So 1 joule is equal to 10 raised to 7 ergs. This is the relation between joule and erg, that 1 joule is equal to 10 raised to 7 erg. Such things you have to remember for the first online assessment in MCQs. It can be asked in the exam. Now we have seen about work. What is work? Force causing a displacement in the object. Now the three types of work you should be introduced to. One is positive work, other is negative work, and the third one is zero work. So what are these three types of work? When the force and the displacement are in the same direction, then the work done by the force is positive. On the other hand, when the force and displacement are in opposite directions, then the work done by the force is negative. Examples, if you want to see, a vehicle which is stuck up, whose wheels are stuck up in the mud. You are pushing that vehicle. Your application of force and the moment, that is the displacement of vehicle, are in the same direction. What you can say, the work done is positive. But you and your friend are playing with a ball. The friend is throwing the ball towards you and you are trying to stop the motion of the ball with your hands. Then the force applied and displacement are in opposite direction. Then the work done is negative. And what is zero work? If a rock is lying on the top of a hill, you are pushing the rock with heavy force but not even able to move the rock by 1 inch also. No displacement is seen even after the application of force. Then we can say that the work done here is zero. So when the applied force does not cause any displacement, or when the force and the displacement are perpendicular to each other, then the work done by the applied force is zero. I hope you have understood all the three types of work. So the name of the chapter is Work and Energy. Now we move towards the next topic for this chapter, that is energy. What do you mean by the term energy? You have seen from a number of examples, the capacity of a body to perform work is called as energy. Energy is the capacity of the body to do work. So here what you can infer is that both are interrelated with each other, energy and work. Both these terms are interrelated. How they are interrelated? To do work, energy is required. And if you want your energy to be wasted, then work has to be done. So both the terms are interrelated with each other. Hence, the units of both energy and work are same. SI unit of work is joule, so SI unit of energy is also joule. CGS unit of work is erg, so CGS unit of energy is also erg. Now you know different forms of energy you have seen around you. The different forms are mechanical energy, heat energy, light energy. From the morning when you get up, different types of energies you are used to. The first is when you go to sleep also, you require electrical energy. Your fans are working, then your ACs are working. In the summer season, when you get up, you heat your water through the heater, geyser. There you get to introduce to the heat energy. Then the sun rises, so you get known to the solar energy, tidal energy from the seas, nuclear energy in nuclear power plants, chemical energies in your, what you can say, crackers and all. Inside your body also chemical energy is present. So different forms of energy exist around you. Out of that, the two forms of mechanical energy we are going to revise here, which is given in your syllabus, that is kinetic energy and potential energy. Kinetic energy is nothing but the energy which an object has because of its motion is called kinetic energy. Because of its motion, because of its movement. I had told you, when a fast cricket ball which is being bowled by the we can say bowler, it strikes the stumps are sure to fall down. Now from where does this ball has acquired this energy? The energy acquired by the ball is because of the fast motion, the movement of the bowler. Or another example is one marble strikes another in a game of marbles. You might have witnessed the game of marbles in your early age. If you strike one marble with your hand, due to the motion of the marble, the energy which is gained by it is transferred to the other marbles and they start moving when it is hit by the first one. So all these examples denote what is kinetic energy. Now expression and all we have already studied, we have revised in our first revision. You all know the formula for kinetic energy, half mv square. Next is potential energy. These are the different examples of kinetic energy. Walking, throwing a ball, flying aeroplane, falling down, all these are examples of kinetic energy. The other form of mechanical energy is potential energy. Energy stored in an object because of its specific state or position is called its potential energy. I have told you, water which is stored in a dam. Dam is at a certain height from the earth's surface. So due to the height, the energy which is stored in water is potential energy. When you release the water from the dam and the water starts falling down, this potential energy gets converted into kinetic energy. How? Because the water has started falling down. So you can see the movement, you can see the motion. Hence it gets transformed into kinetic energy. So the different examples are water stored in the dam or a compressed spring. All these are examples of potential energy. Quickly we will see its derivation. For potential energy, we are going to consider an object of mass m carried to a certain height h above the earth's surface. If you want to derive the expression for potential energy, your object should be at a certain height. It should be at a certain position. So, a force equal to mg has to be used against the direction of gravitational force. When you are lifting any object from the earth's surface, you are acting against the direction of the gravitational force which is exerted by the earth. So, the force here is m into a, which is nothing but m into g. Amount of work done can be calculated as follows. Work is what? Force into displacement. What is the force applied here? mg. What is the displacement? Displacement is the height h to which the object is raised. So work is mgh. Now the amount of potential energy stored in the object is because of its displacement, because of the height. So here work done, you can call it as potential energy. So potential energy is nothing but mgh. So the formula for kinetic energy is half mv square, whereas that for potential energy is mgh. Now the next topic is law of conservation of energy. These are the different examples of potential energy: raised object, stretched spring, battery, dynamite. All these are different examples. Law of conservation of energy. What does it state? Energy can neither be created nor destroyed. It can be converted from one form into another. Hence, the total amount of energy in the universe always remains constant. Just now we had seen the example how water which is stored in the dam, potential energy getting converted into kinetic energy. I had taken a very good example of ice which is in the solid state. When you just heat it or keep it at the room temperature, it will get converted into the water stage. When you heat the water, it will get converted into steam. So you can see that here the water, it is not getting, neither you can create this water nor you can destroy it from the universe. Only you can convert it from one form to another. So that only you can apply here for energy. One small activity we had seen over here. Make two pendulums of the same length with the help of the thread and two nuts. tie another thread in the horizontal position. Tie the two pendulums to this horizontal thread. You can see here two threads which act as pendulums with two nuts over here in such a way that they will not hit each other while swinging. Now swing one of the pendulums and observe. What will you see? As the speed of oscillation of the pendulum slowly decreases, the second pendulum, which was initially at rest, which was initially stationary, it begins to swing. Thus, what is the case here? The first pendulum, which was made to swing, it transfers its energy to the other, due to which it starts moving. So here you can see the transformation of energy. Many examples we have seen over here when the explanation of the chapter was done. How in the case of generator, mechanical energy gets converted into electrical energy. Or with the case of fan or an engine, electrical energy gets converted into mechanical energy. Loudspeaker, where electrical energy is converted into sound energy. In the case of primary cell, your chemical energy gets converted. So the n number of examples we have seen. Go through the examples. It can be asked under MCQs. And the last topic to wind up our today's revision is power. Power. What does power mean? It is the rate at which work is done. We had seen the example of you and your father climbing the stairs. Who will climb first? Surely you. So what is this power? Power is the rate at which work is done. Work done is same of climbing the stairs, same floor, but due to the age factor, your father will take more time for the same amount of work, which you will complete it very early because of your young age. So what is power? The rate at which work is done. So if W amount of work is done in time T, then formula for power is work upon time. You all know work is denoted by capital W, time in T, and the SI unit of power will be joule per second. Why SI unit? Joule per second, because SI unit of work is joule and time you know it is second, and joule per second is also called as watt. Now you all know about the steam engine, which was invented in the year 1781 by the Scottish scientist James Watt, and this invention it really brought about an industrial revolution, and unit of power is called watt in his recognition of work. And James Watt was the first to use the term horsepower. So 1 watt is nothing but 1 joule per 1 second, and 1 horsepower is nothing but 746 watt. Remember the conversions for your exam. Now the unit of energy for commercial use, for commercial purpose, is kilowatt hour. 1000 joule work performed in 1 second is nothing but 1 kilowatt hour. So 1 kilowatt hour is nothing but 1 kilowatt into 1 hour. 1 kilowatt is how much watts? 1000 watt. 1 hour is 3600 seconds. So here you can see the conversion in joules, which you also call it as 1 kilowatt hour is 3.6 into 10 raised to 6 joules. And 1 kilowatt hour is nothing but 1 unit. And I had told you, when you get the electricity bill in your houses, just go through the bills. In the center you will see the number of units which are consumed by you. At least 6 months consumption you will get in the electricity bill. So there you will come to know in the month of January how many units you have used. In the month of February how many units you have used. And then you can say the bill is decided on how much is the amount, how much is the rate per unit. Suppose per unit it is 10 rupees charged by the electricity department and your consumption is 3 units, then 3 multiplied by 10, you will get 30 rupees bill. If your consumption is 40 units, then 40 multiplied by 3, 120 rupees. So per unit, whatever is the charge, multiply by the consumption per month, you just calculate and you see, you will get the on what basis your electricity bill is sent to you. And who finds out about these units? You know, every month there is the meter reading which is taken by the electricity department. They send the person in your building, in your houses, they take your meter readings and then they calculate the bill and send it to you. So all these things which are your practical applications, you should know it. I think we have completed with the revision for both the chapters of section A and section B very thoroughly. Twice we have completed with the revision part. So I don't think you have any doubts regarding your first online assessment. Read the chapters thoroughly before attending your assessment exam. See to it that your books are completed, your journal is completed, and best of luck from my side to all my dear children for your first online assessment. Thank you.